So focus on 24. We want to find the work required to pump the water out of the spout. We're going to assume that the tank is full of water in this case. Okay, so how do we do it? Draw a good picture first of all. So what you're going to want to do, this is a spherical tank. Even though it looks like a circle, it's supposed to be a sphere, right? Obviously a circle can't contain water. So what you want to do is draw a cross section of that spherical tank. A cross section that goes through the center of the spherical tank, so that you will have a circle in the picture that you draw. So let's do that. Okay, and then the spout is up. What would the height here be? If the height here is 3, what would the height here be? 4. Yeah. And then, so the spout, draw that so you don't forget about it, because that's going to be important. Okay. So imagine the tank is full of water. So I'm going to draw the ith slice of water, because what we're going to do is find the work done, at least to start, we're going to find the work done in pumping out the ith slice of water. So from this perspective, the ith slice of water is actually going to look like a rectangle, of course. But what is it actually? If you looked at it from above, wouldn't it be a cylinder with height, I guess delta y, the way I've drawn it, right? If you looked at this from above, so remember, this is a sphere we're dealing with, then that slice would actually be a cylindrical slice. That's important to know, because we're going to need to find the volume of that slice. Okay? So keep that in mind. So here's your ith slice of water. Okay? Well, maybe I shouldn't draw those in. Those might get in the way. But I will say this. We're going to end up thinking of the interval that coincides with the ith slice on the y-axis. We're going to think of that as our ith interval. And we're going to pick a y sub I sample value from that interval. So I'll label that right now. And you'll see what we use that for in just a little bit. Okay, so the idea then is to find W sub I, which I'm going to write it out in English so it's clear. It's the work in pumping out the ith slice of water. In this case, these slices are cylindrical in nature, but they're not all the same size. It depends on their height as to what size they are, because they have to fit inside the sphere, right? Okay, well, back to the old formula again. W sub I is equal to what? W equals force times distance, so I'm just going to put in some subscripts, right? F sub I times D sub I. Okay. Now, what this breaks down to, the force, isn't that actually going to be just the weight of the ith slice? Isn't that what the forces have been in the other problems as well? Not with water, but with other things. So just to make this explicit, F sub I is the weight of the ith slice of water. D sub I we'll talk about, it's not as hard to get D sub I, we'll talk about that in a couple minutes. So that's also force times distance right there. So let's concentrate on getting the weight of the ith slice of water. Now, let's start with what you could call I suppose the density it would be of water. Does anybody know what the density of water is? It's around 1,000 what would the units have to be in if it's density? It'd be in, I suppose it'd be in kilograms, right? Mass over volume, kilograms per cubic meter. So that's what that is. I'm not going to write those units down, but in case you're curious. So it would be 1,000 kilograms per cubic meter, but that's a measure of mass per unit volume, right? How do we turn that into a weight density, if you like? So let me put off that step just so you can, I want to belabor this just so it's not so confusing in the future. Okay. So what I'm about to find is what I would call the weight density. Right? But that would just be of 1 cubic unit. So you'd have to multiply that. To get it to be the total weight, you'd have to multiply that times the volume of the ice slice. So this would be weight density of ice slice, if you like. And volume of the ice slice. Together, you multiply those together, and that product would be the weight of the ice slice. So together, that would be weight of ice slice. Does that make sense? Of water. All right. So now back to what I was talking about. Just so it's perfectly clear. Okay, the weight density of the ice slice. Well, okay, the mass is 1,000 per cubic meter, 1,000 kilograms per cubic meter. But what would I have to multiply that to turn that into a weight measurement? This is the same as before. It's mass, force, or weight equals mass times acceleration, or in this case, the acceleration due to gravity. So it would be 1,000 times 9.8. That's just the weight density, okay? So it's 9,800, and if it's just regular water, it'll always be 9,800. But if it's a different substance, you're going to have to go through this calculation, right? Because it'll change from 1,000 to maybe for gasoline less than 1,000. Okay, and then the volume, we'll keep the volume part the same, volume. And then again, we have the d sub I. Is that clear? All right, so now we're on the right track. So we're going to get, what, 9,800 for that first part. Now, this is where we have to put in our thinking caps. The volume of the ice slice. Let's go back to the picture. This ice slice is actually cylindrical. Let's make a note of that. Okay. And its height would be, I guess, delta y, if you like. Okay. In general, what's the volume of a cylinder? Pi r squared h. Well, we know the h part of that. Delta y is the h part of that. We need to get, then, I guess, pi r squared h. We need to get the r part, the radius of that cylindrical slice. So would you agree that the radius, then, would just be this distance? I'm going to erase this in a second, so pay attention. It would just be this distance out to here? Wouldn't that be the radius? Okay. Well, this guy in green here is the graph of a circle, a radius 3 centered at the origin. You can put your coordinate system wherever you want, but doesn't the circle have the simplest equation when you center it at the origin? So that's the reason I did it the way I did it. Okay. What's the equation of this circle? well, let's start from first principles here. What's the generic equation, or not quite generic? What's the full equation of this circle? X squared plus y squared equals r squared would be generic. And in this case, what is our r going to be? Well, you're right. And then when you square it, what do you get? 9. Okay. I meant to say r squared. But you're right. I just said r. Okay, now we're dealing with horizontal slices here. So are we going to think y is a function of x to get out to the curve, or x is a function of y? Horizontal slices, we want x as a function of y. So that means if you solve this for x, what do you get? I suppose you do have plus or minus. We're only going to take the plus part of it, but you're going to have plus or minus the square root of 9 minus, well, y squared actually, because I'm solving for x. Make sense? Okay, so let me redraw that radius then. That radius then would be that distance, right? We'll call that r, or the pirate would say r, and like pirates did calculus. What is that? Well, you don't need the plus or minus part, right? Just the plus part. So square root of 9 minus y squared. Make sense? Now, if those were blocks, if that rectangle corresponded to a block instead of a cylinder, then you would need the entire length all the way across to help you find the volume, right? To multiply the dimensions together. But you could just double that square root of 9 minus y squared, couldn't you? To get the total distance all the way across. That's not the case here, but in other problems it might be the case. So you have to think, what shape is your slice to get its volume? And you have to use those well-known geometric formulas that that frankly you might have not used in a while, and you might not be thinking about off the top of your head. Okay, so now we're in business. So the volume then of the ith slice, which you could call v sub I, would be what? Okay, you guys already told me pi r squared h, but what is that? In this case, it would be pi times, right, square root of 9 minus y squared squared. That's your r squared, right? And then the h is just delta y. Now we're in business. Okay. So that's going to be the volume of your ith slice. So let's go down here and fill that in. So that's this portion of it right here. So pi times r squared times delta y, where r was the square root of 9 minus y sub I squared. And then I'll simplify that in the next step. What is d sub I going to be? Let's go back to the picture. Really, I guess it would be a y sub I here being squared. Let's go back to the picture. How far am I moving this ith slice? It's being pumped out the top. Well, you're close. So here's the top, right, at 4. And so about how far are you moving this ith slice? Well, just think of it in terms of measuring a distance. You take the bigger number minus the smaller number. In this case, the bigger number is 4, and the smaller number is actually just the height of this ith slice, which is given by the y sub I. So 4 minus y sub I. Now some of you are, and this is what I thought the first time I saw these problems. Or maybe not the first time, but after I understood these problems, this is what I thought. That's not really what's happening. If you've ever seen a pump, it doesn't break up water or liquid into slices and pump out individual slices at a time, no matter how small you get. And also the fact that it has to fit through that little nozzle at the top tells you that. Okay, but the energy used or the work done is equivalent is what we're saying. So yeah, physically it doesn't work this way, but we're calculating the work done, and this is a way to model that, not the actual physical process of how the water is moved through the pump. Okay, so that's the distance. So that's the d sub I. And then let's clean it up. I get 9,800 pi, pi. And then I'll just have, I guess I need parentheses around it, the square root of 9 minus y sub I squared times, I'm going to write the quantity 4 minus y sub I next, and then I'll put the delta y on the end. And that is definitely the hard part of this problem. That's why I belabored it so long. The total work done would involve an integral, right? Over all such slices. Can I pull the constant out front? Would that bug you too much if I did that right away? So what's the constant I can pull out front? 9,800 pi. And we're integrating from what to what? So where can you put in a slice? From -3 to 3. So you're not including the nozzle in that. It's the region of integration, which is inside the circle. So from -3 up here to +3 up at the top. Okay, so -3 to 3, and then what does the integrand become? Just 9 minus y squared, right? As a quantity times the quantity 4 minus y. If you don't multiply out the pi, it's 1,411,200 times pi. So that's all one number. You might put it in scientific notation, that's so large. And then what units are we in? Remember, our measurements were in meters, so we better be in joules.